Professor R. Asokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
We have been going through a set of lectures on crystal structures and properties of materials for the electronic students. Now, in this lecture, in continuation to what we have been discussing on the symmetry and physical properties, I will be continuing with the same thing. The contents of this lecture are symmetry and physical properties, especially I will be talking about piezoelectricity as the best example, problems, Miller indices and its significance, Miller indices of certain crystallographic planes. I mentioned to you in the previous lecture, if you take a piezoelectric crystal in the uncompressed state, when it is left to itself, right, in the normal state, the charge centroids of the ions that you have got here, that is the positive ions, as well as the charge centroids of the negative ions, the two charge centroids coincide, as a result of which the crystal will be neutral, it is not polarized. What Pierre Curie observed was, when you apply stress to a crystal, suppose you assume this to be the crystal, when you apply pressure on both faces, then the crystal acquires some kind of polarization, or a field is produced along the two faces, or a voltage is developed, right. You have to understand as to how the voltage is developed. Now, you look at this picture corresponding to the sigma that you have got. What is sigma? Sigma is the stress applied. When you apply a stress to the crystal, right, you look at the hexagon that you have got here. Now, you compare this hexagon with this hexagon. What do you observe now? This white atom or the ion has moved in, right. What is this white? The positive ions have moved in, and negative ion has also moved. So, the unit cell, unlike what it was earlier, the unit cell has been somewhat distorted. You had a nice hexagon, that symmetry has been broken to the certain extent. What I would like to convey to you, the charge centroids do not coincide any longer. You see here a dot here, this dot with plus q here, the positive charge center that you have got here, the center of this triangle which connects the atoms 1, 6 and 3, the charge centroid is here, whereas the center of gravity like charge centroid of the negative ions you have got here. The important point is the charge centroids were coinciding earlier in this picture, when the material was not subjected to any pressure. Now, on the other hand, when you apply some pressure, the ions move, obviously the ions should move. in the unit cell, the ions move, as a result of which the charge centroids are separated by a distance d, giving rise to, how do you visualize the situation? You got a charge here, another charge here, separated by a distance d. Because of that, the dipole moment mu will be equal to the charge times the displacement. So, the separation of charge centroids under stress, it gives rise to an electrical dipole moment. Now, the crystal is polarized, the positively charged, the negatively charged, then there will be a voltage developed, right. That is what is happening here in a piezoelectric crystal. So, the unit cell acquires an electric moment, and hence the crystal as a whole is polarized. It will be understood that the crystal lacks inversion center. The most important point I would like to stress, the crystal lacks inversion center. It is a non-centrosymmetric crystal. What do you understand by this? Now, you see, as I told you in the earlier lecture, for a ion here whose coordinates are x, y and z, there should be a similar ion at minus x, minus y, minus z, that is at this point. Now, that is not there. You got a ion here, a negative ion here, right. This is a dark circle refers to a negative ion, that is here. Here this region you do not have a negative ion, you got a positive ion. That is the reason why I am telling that this crystal lacks inversion center. The most important point to be understood is, if a crystal were to be piezoelectric, it should be non-centrosymmetric. Now, this crystal acquires a dipole moment because of the fact that you do not have similar ions. For every ion you have at x, y, z, you should have had an ion at minus x, minus y, minus z, if the inversion center should be present. Because you got a ion here, a different ion here, the inversion center is absent, or it is a non-centrosymmetric crystal. Because it is non-centrosymmetric, that is the reason why the charge centroids are separated, thereby the crystal acquires a dipole moment. The unit cell of every crystal will acquire a dipole moment. The crystal as a whole acquires a dipole moment. Hence, a crystal were to be piezoelectric, the unit cell should be non-centrosymmetric. Conversely, as I told you in the earlier lecture, if an alternating voltage is applied between the two faces of a quartz crystal, it will begin to vibrate. When you apply pressure, the two faces come nearer to each other. When you release the pressure, they will go apart, they will go back to the equilibrium positions. Now, during this compression, a voltage is developed, right, as I told you in the previous lecture. Now, on the contrary, you apply a alternating voltage, what you observe is the so called inverse piezoelectric effect. Again, the significant point which I would like to stress is, we are not interested in the piezoelectric effect as it is, we are interested in the inverse piezoelectric effect, right. The inverse piezoelectric effect alone gives rise to the ultrasonic waves, using which you make use of sonar or biomedical devices to detect gallbladder stones, or even to see the sex of the baby. In a period of 3 months, the sex of the baby can be determined by using ultrasound. So, the production of ultrasonics is a very powerful technique which can be used to detect the defects in automobiles, in railways, in aircrafts, not only in the area of material science, but also in biological systems also. The, as I told you, the sex of the baby and very many problems can be detected using ultrasonography. It is important to note that the centrosymmetric crystals cannot exhibit piezoelectricity. Only non-centrosymmetric crystals will exhibit piezoelectricity. So, this is a very important point. Gallium arsenide, a 3,5 compound, is also based on diamond structure, but the two basis atoms are different. One is gallium, the other is arsenic. The diamond lattice has the center of inversion, whereas zinc blende does not have it. The important point is the absence of the symmetry element, inversion center, in crystals like gallium arsenide alone will exhibit non-linear optical properties, and hence is of great importance. So, apart from barium titanate or other crystals which are non-centrosymmetric, which exhibit piezoelectricity. In addition to piezoelectricity, I am now talking about a semiconducting system like gallium arsenide, that also lacks inversion center. Because of the fact that it lacks inversion center, the absence of inversion center, right, that is the reason why it is very much used in non-linear optical devices, right. It is of great importance. And again, every symmetry element can be represented by a matrix. Now, all the symmetry properties can be mathematically represented. There is a big area called group theory, right, wherein you have very many theorems and so on. And so, essentially what I would like to tell you is every symmetry operation can be given a matrix representation. Now, it is a child's play. At a young age, one can tell which matrix will take x, y, z to minus x minus y minus z. It is a unit matrix obviously, right. Supposing x, y, z ought to be taken to minus x minus y minus z, then in such a case along the diagonal elements you will be having minus 1 minus 1 minus 1, which will take your x, y, z to minus x minus y minus z. So, for inversion to take place, you have to have an operator at the unit matrix, where the diagonal elements all will be minus 1 minus 1 minus 1. Okay. If one asks the question, what is the matrix which represents inversion center, which by which x, y, z can be taken to minus x minus y minus, that is the inversion, right. Inversion operation to be continued, then in such a case that can be done by a unit matrix, wherein the diagonal elements will not be 1 1 1, but minus 1 minus 1 minus 1. Okay. I have been stressing about non-centrosymmetric crystals, that alone can be piezoelectric. It does not mean all non-centrosymmetric crystals should be piezoelectric. On the other hand, if piezoelectricity is to be observed, the crystal should necessarily be non-centrosymmetric, but the converse is not true. Okay. That is important again. Then we go to some of the problems in basic crystal structure, wherein we all know density is equal to mass by volume. Mass is the number of atoms per unit cell multiply mass of each atom. Mass of each atom will be atomic weight divided by Avogadro's number. Now, this is a fundamental expression, right. The theoretical density rho is given by an expression of this kind, where you got n into A in the numerator and V c into Na in the denominator, where what is n? N is the number of atoms per unit cell, A is the atomic weight given in terms of grams per mole, and in the denominator we have got V c, that is volume of cell, right. A centimeter cube per unit cell will be the dimension for the V c. Na is the Avogadro's number, whose value is well known, 6.023 into 10 to the power of 23 atoms per mole. This is the expression which is to be used to determine the density of any crystal, right. So, when you are talking about crystal structures, how will you determine the density? For that, these are the things which are to be known. So, the simple expression is N E by V c into N A. Okay. Now, let us take the case of copper and see how this can be used to determine or calculate the theoretical density rho, right. It is called the theoretical density because it will not be exactly equal to experimental or measured density of a given material. Now, let us look at the case of copper. We will calculate the theoretical density of copper, the estimation of theoretical density of any given crystal. It is given by a formula of this kind. The theoretical density is given in terms of the product of the number of atoms per unit cell multiplied by atomic weight divided by the volume of cell multiplied by the Avogadro number. That is the same thing I have got here, right. Now, let us take the case of copper. This is a general formula obviously. Now, the data are given William Callister's book. The crystal structure, if FCC, the number of atoms per unit cell obviously for a FCC structure, you know, you got 8 atoms at the 8 corners contributing to 8 into 1 by 8. Then there are atoms at the face centers, 6 faces, 6 into half, that is 8 into 1 by 8 plus 6 into half, that makes 4. So, the number of atoms per unit cell will be 4, obviously that is known by now, you will be very well aware of it. Then the atomic weight is 63.55 grams per mole. The atomic radius will be 0.128 nanometer. So, the volume will be given as A by 4R by root 2. To find the volume, you should be knowing the cell dimension, the value of A, the size of the unit cell should be known. We have seen already when we calculated the atomic packing fraction, we had a relation between A and R in the hot sphere approximation. That is what we are using here. A will be 4 into R by root 2, making this volume to be equal to 4.7. A cube will be volume, right. So, A is here. So, when you are substituting this R here, your A cube will be the cell volume, that will be equal to 4.75 into 10 to the power of minus 23 centimeter cube. So, upon substituting for V c, then the Avogadro number, the number of atoms per cell is 4, the atomic weight is given here 63.55. Upon substituting all these values, you end up with the theoretical density, which is 8.89 grams per centimeter cube. Now, that is obviously in very good agreement with the actual value of the density of copper. Rho copper will be 8.94, that is experimental value, right, 8.94 grams per centimeter cube. Okay. That is how one estimates the density of any given material. Now, this is a very general formula which can be applied to any crystal. We will move on to yet another simple problem. Now, that is what we have been talking about, the theoretical density and the actual value, all these things are given once again for copper. We will move on to estimate the lattice parameter. It is a worked out example, the lattice parameter of copper again. Copper crystallizes in FCC structure, as we all know, we have seen in the previous problem, and an atomic radius of copper is 1.278 angstrom unit. Calculate the lattice parameter and hence the cell volume. As we did in the last problem, the cell dimension A will be equal to 4R divided by root 2. Radius of the atom is 1.278 angstroms. So, substitute the radius here. Upon substitution, you will have the A value to be 3.61 into 10 to the power minus 10 meter. That is the cell dimension, that is the value of A. Obviously, A cube will be 47.04 into 10 to the power of 30 per meter cube. That is what you will be having as the volume of the cell. With this, of course, we try to finish more or less some of the things that we have been talking about with the crystal structure, and we have been referring to the crystallographic planes, the importance of planes. I told you about plane of polarization that comes in optics, then the plane in which the mechanical deformation will easily occur. When you talk of mechanical deformation or elongation of material, right, when you apply have a wire or a metal or alloy in the form of a rod or whatever shape, when you apply stress, there will be elongation or the material is getting deformed, the deformation, the mechanical deformation again depends upon the crystallographic plane. Just now we saw the piezoelectric effect when I mentioned about the electromechanical coupling coefficient, that is that plane across which when you apply an alternating potential, the efficiency of conversion of the electrical energy into mechanical energy, in which plane it will be maximum, right. Now, these are some examples why you should be interested in the crystallographic planes. Now, what is a crystalline plane? What is a crystalline plane is nothing but this is a plane, right. As I told you earlier, this is a crystalline plane, there is another plane and so on, and again the planes will not be the same in the sense you have one plane here, the another plane may be passing through the body centered cubic structure, a plane may be passing through the body centered cubic. This is yet another plane. So, every plane need not be containing the same number of atoms. How to represent these planes? It was given by Miller, you got the Miller indices. The credit actually should have gone to Miller's teacher. It is Miller's teacher who taught Miller as to how to represent any given plane. So, crystalline planes are represented by Miller indices. The planes and directions are important, as I told you. The directions also are important in the earlier lecture, that is a double refraction and then what easy and difficult direction of magnetization and so on. Various anisotropic properties can be applied on the basis of the atoms in the different planes. Now, depending upon the number of atoms, the mechanical deformation occurs in different materials. It is a mechanical property, right. From the mechanical property point of view, the deformation occurs along those planes which are closely packed. That means, when you have more number of atoms in a plane, or we talk of planar density. When you are talking about a particular line, how many atoms are there, it is called a linear density. We talked about density of copper and so on, it is a volume density. Then you can talk of atoms in a plane. As I told you, if you have got atoms here, there are 4 atoms in this plane. On the other hand, if you have got a plane which is passing through this and this, then there will be 5 atoms. Therefore, the planar density is different, right. The number of atoms that you have got in a plane, in different planes it will be different. The planar density, what I would like to tell you is, if the density, the planar density is large, then the crystal will deform, right. The mechanical deformation will be easier along that plane which has got higher planar density. So, very many properties depend upon crystalline planes. That is the reason why we study Miller indices. Piezoelectricity is one problem, the electromechanical coupling coefficient I am talking about. Then it depends upon the plane across which alternating voltage is applied. Mechanical deformation takes place along those planes which contain more number of atoms, that is slip plane. I told you about plane of polarization optics. This is how one obtains Miller indices. Look at this plane, right. You have got a crystal here, this is the plane I am talking about. As to how to represent this plane. Now, what happens to the plane? Now, you have a plane which makes an intersection at 2 times A, right, and the Miller indices are defined by taking the intercepts of the plane with the cell vectors. The intersection occurs at 2 times A and 3 times B. There are the 3 mutually perpendicular directions A, B, C, and 2 times C. So, the intersection takes place at 2 A, 3 B and 2 C. So, the intercepts are, you forget about A, B, C, then you write 2, 3, 2. We take the inverse of it 1 by 2, 1 by 3 and 1 by 2, then you take a LCM. The Miller indices are the lowest set of integers which have the same ratio as the inverses. So, that means you have to have 3 into 2 6, 6 divided by 2 will be 3, 6 divided by 3 will be 2 and again 6 divided by 2 will be 3. So, 3 2 3 is the Miller indices of this plane, right. We will have a few more examples, right. So, before going further, let me tell you the steps, the procedure adopted to determine the Miller indices. Determine the intercepts made by the plane under consideration on the 3 coordinate axes. The 3 coordinate axes are A, B, C, you have got A here, B here and C on the 3 coordinate axes. Mark these intercepts as P, Q, R. Convert these values P, Q, R into fractional intercepts by dividing with their axial lengths, that is P by A, Q by B, R by C, where A, B, C are their axial lengths of the unit cells. Find the reciprocal of the fractional intercepts, that is A by P, B by Q and C by R. Convert these reciprocals into smallest set of integers. Name these values as HKL. In general, without any comma, you write HKL. HKL refers to the Miller indices. This notation HKL represents the Miller indices of the plane under consideration. Okay. Then you have a plane here. Now, what do you observe? It makes an intersection along the A direction. It is making intersection 3 times A, 2 times B and 2 times C. Okay. This is the plane. The intersections are made 3 times A, 2 times B and 2 times C. So, how will you write 3 2 2, right, the intersection. So, 3 times A, 2 times B, 2 times C. So, you write 3 2 2 and take the reciprocals, that is 1 by 3, 1 by 2, 1 by 2. Then you convert them, you take the LCM, the smallest 3 integers having the same ratio, that is again multiply with 6, 6 by 3, that means 2, then 6 by 2, 6 by 2, 2 3 3, right. So, 2 3 3 is the representation which is given to this plane. So, this plane will be called as a 2 3 3 plane, right. This is not a single plane, it refers to a family of planes, right, all planes which will be parallel to each other, because you are taking LCM, right. So, all planes which are parallel to this plane will have the same indices 2 3 3. So, it refers to not to a single plane, all the planes which are parallel to each other. Let us look at the cubic structure and how you talk about various planes. Let me summarize the important points. Or Miller indices are used to refer to the planes in crystals. They are important as many properties are dependent upon the planes. For instance, piezoelectricity and mechanical deformation, which have been talked in detail, are some of the examples. Any plane or family of planes parallel to each other are represented in terms of the same 3 integers HKL. Let me now pass on to the question session. What is the matrix which will represent inversion symmetry? What are Miller indices? How are they obtained? With this, we close mostly the section on Miller indices, and we will see the Miller indices in cubic systems to a greater extent in the lecture to come. Thank you.